Hi, this is Lucas, and I'm presenting my final project for CSCI e63 Big Data Analytics in spring 2017. My project is on TensorFlow and neural networks for visual art generation with applications to Deep Dream. So I will hopefully have some time to go through the general architecture of Inception, why it was useful, and showcase some really interesting neural artwork that looks very hallucinogenic. So this demo will demonstrate two approaches to generating hallucinations. The first is feature specific. By that I mean we pick a layer in the CobNet and we describe exactly what feature we want the network to amplify. So that can be thought of as the feature channel that might respond very highly to bananas, whereas another feature channel might respond very highly to dogs, or at a low level could be lines or circles or whatnot. And this is very similar to how our visual cortex works. The second way that we can generate hallucinations is layer specific. You can think of it as just an aggregation of the feature specific approach. Instead of specifying a particular feature channel, we just say maybe average the entire activations across an entire layer, which could have maybe dozens or even over 100 different types of feature channels, and let the network decide what it likes or what combinations of features it likes, and then amplify that. Regarding applications, this demo will then apply feature-specific and layer-specific Deep Dream to a randomly generated image and also a real high-resolution image about the Northern Lights. So regarding my data indirectly comes from ImageNet, which is a product database containing over 10 million images that have been hand annotated by humans. Since 2012, they host an annual object recognition contest that has become the standard for benchmarking image classification algorithms worldwide. And in 2012, AlexNet, which is a very famous architecture in the deep learning community, resulted in a huge performance gain in the 2012 edition of the ImageNet competition, which indirectly, or I guess directly, ushered in a new wave of deep learning research. A couple years later, GooglyNet, which is a more complex and effective version of AlexNet, also known as Inception, achieved a new state-of-the-art for classification and detection. And the details of this model are in the paper Going Deeper with Convolutions, published by Google Research. The main innovation here was not only was it more accurate, but it also improved the computing resource utilization inside the network due to this thing called the Inception module, which is really just a type of multiprocessing convolutional operation that enables greater depth and width of the network. So you can see more different types of features at different scales and do it without exploding your computational cost. So what is the Inception module? It increases the number of network layers without imposing a large increase in complexity. They do this through dimensionality reduction via one-by-one convolutions. So you can kind of skip out on some math and minimize the number of input filters that one has to compute from one layer to the next. You can see some of the visualizations below that explain this concept, and I explain it more in my report. But another important takeaway is instead of selecting which size convolution you want, for instance, using a 3x3 kernel or a 5x5 kernel or a 1x1 kernel, you can just use all of them. And also add in max pooling while you're at it as well. So you let the network learn what resolution is most effective at classifying your output. And this is, I guess, intuitively makes a lot of sense because visual information should be processed at different scales and then aggregated so that the next stage can abstract the relevant features. And finally, networks are usually 2 to 3 times faster that use the Inception module than networks that do not. So this was really, really great. It's also pretty well documented at this point. It's been a couple years, so it's a really good example to walk through. So now I'll go through kind of the steps of my code, and we can start here. So step one is generate do all your imports. We use TensorFlow, NumPy for numerical computing. We generate some random numbers, some basic adding, subtracting, and then we have some image manipulation libraries. Feel free to use pip or pip3 install if you lack any of these libraries. You can run that right here. The second step that one can do is import Inception. So I'm not actually training Inception. That requires very expensive GPUs over possibly weeks of time, and you would basically crunch millions of images to create a well-trained layer that's very effective at distinguishing over 1,000 different classes. That's not really what we're trying to do here. We're actually trying to take a pre-trained network and then cause it to hallucinate by sort of inverting the process. We really want to look at an input image and change the input image based off of what layer that's already been pre-trained within Inception activates. So we can use a pre-trained one. So the Inception v1 variant, also known as Inception 5H, is really easy to use for Deep Dream because the inputs can be of any size, and according to a lot of folks online, it seems to be that the images actually look better than later architectures. So feel free to use later architectures, but Inception v1 works really well. In my paper, I think I linked to one of the, yeah, this is the checkpoint, but there's other checkpoints online that you can also download. So once you import Inception, and here's some helper functions that do this, you need to download the actual protocol buffer that contains the graph itself, so all those crazy layers, and this is the URL in which you can download it from. And then here, once we create an Inception module, which is just kind of or this class is just kind of a wrapper around the actual graph definition, I added some helper functions that spit out the number of layers, something that gives the name of the tensor by the layer. This will be useful later. Something that feeds in an image, because we need to feed in an image to our pre-trained network, and something that also calculates the gradient. It's actually wicked simple to calculate the gradient because TF has a operation called TF gradients. So that would just be terrible to compute by hand. You'd have to do a lot of partial derivatives. It would be terrible. So once you import Inception, you can do right here. You can maybe download it. If not, create an instance of the class, and to make sure it works, you can print the number of convolutional layers. This time it's 59. So once you download it and print it, you're all good. So the core thing here are the layers themselves. These layers are what you run Deep Dream on, and you say, hey, Deep Dream, recursively change your input image based on the layer's maximum average activations of a layer, or a corresponding set of features, and give me something interesting. So if you print out model tensors, you can see the 59 layers. You don't need to know really what each one does right now. Just the important thing to keep in mind is the number of featured channels or feature maps, depending on the language that you use. At the low levels, there's no fancy Inception modules. Once you see these like mixed 5x5, mixed 3x1, or 3x3, or 1x1, these are all the Inception modules. And then at the very end, you have your fully connected layers that do the actual classification. So great, this is great. We now can access these tensors that we want to incept. So here you go. So this is kind of our key. This is what we're using. Step 5, I defined some helper functions that help us with image manipulation. These helper functions are pretty basic. They save stuff to disk and plot our gradients and resize our images. Pretty standard stuff. You can load them here. Also, they do some normalization because we want to make sure all pixels are all between 0 and 255. And then finally, we want to implement Deep Dream. That's where the fun happens. Intuitively, let's say you have a channel that really likes bananas. Let's say it's channel, mixed 4D, 3x3 ReLU. I want to say, oh, this is the banana channel or the banana layer. Change an image of random noise and continually create more banana-like features. So when I feed it again through the model, it lights up that banana channel, and the banana channel gives me really high scores. So it's kind of like saying, in your eyeball, one neuron might fire when you see a certain line in orientation. There's a famous experiment about that, and you want to make sure that what you look at maximally fires that particular neuron. These researchers got really creative, and they also said, well, why don't we just apply this to actual images? And then the neural network will pretend to see certain patterns within the image based on the gradient of pixels, and then hallucinate new shapes and patterns within it, just like a kid looking at clouds and they see animals or shapes in clouds. So step 6, at a high level, this is kind of what we're doing. So Inception 5H can take images of any size, but the bigger images requires more RAM to process because you're doing more convolutions across a bigger matrix, and each matrix has pixel values. So to reduce the RAM, we randomly split the input image into smaller tiles and calculate the gradient for each tile. We randomly split them so the gradient borders don't become refined. If you split it 4 ways each time, then there would be probably like this cross shape in your image. You don't want that. So next we optimize. The optimize runs function runs a loop that just executes the deep dream algorithm over and over and over again. So it says, given a layer in the inception module, the gradient's computed with respect to the input image. Then we add that gradient to the input image, so the mean value of the layer tensor is really high. For channel specific cases, same thing, except you just pick a specific channel instead of the entire layer, and you do this over and over and over again. And Deep Dream will amplify whatever pattern the inception model likes to see, because you feed it these increasingly psychedelic images over and over and over again. Great. Unfortunately, Inception was trained on tiny images. We might want big ones like internet backgrounds for our laptops. So there's another helper function that recursively downscales the input image, and it runs each downscaled version through optimize images. So optimize images is the thing that actually does all the work for us. And there's some hyperparameters around, like, number of iterations you want or the step size. Important point about the step size: unlike gradient descent in most machine learning, we are actually doing gradient ascent because we are trying to get higher scores, higher activations. So we say for every gradient, multiply that by a big step, and the bigger the steps, the more hallucinations you'll get. Great. So finally, we can execute Deep Dream. You want to start a session. Oh yeah, another point about the recursively downscaling, we also blur the gradient with different amounts, and then we add each blurred gradient together. So all that's saying is, like, we want to smooth out our gradients because we don't really care about the precise pixel location. We just care about the general pixel location, and we want kind of smooth images, not rigid or kind of hard or harsh images. So you can use a Gaussian filter, which just smooths out the gradient pixel values, and then you add it to the old image, and then boom, you have a smoother image. So step 7, execute Deep Dream. We can start a session. This is really good for Shell or Jupyter notebooks. Jupyter notebooks are great for things like this because you can just like visualize stuff really easily in cells, and you don't have to worry about starting programs or running Python run or make something over and over and over again. So great. So the first result that I have, I just wanted to look at layer activations. I don't care about the specific channels. I want to just look at the entire thing. So here I picked conv2d1. This is before the inception modules, and I also made an image of random noise which is a square, 600 by 600. So what we should see is in step size 7, so it's pretty big step size. We're not going to blend it with the old image, so it's like a little smoother. I'm going to rescale it by 1/7 each time until it reaches its original size of 600. So what you'll see is at each step, it processes this image, and then the hallucinations become deeper and deeper and deeper. Apparently, this layer really likes these linear-like patterns, these kind of straight lines and shapes, and that makes sense because it is a lower-level layer. Lovely. And it takes a little while to run on a brand new MacBook Pro. For the sake of time, you can trust me on this one, but if I were to generate another random image and use a mid-level layer, Mix3A, which is a inception layer, and I give it all the channels, I give it a little bigger step size, and this will eventually print out flower-like patterns. So it looks like this layer really loves these interesting wavy flower-like shapes. And because I kind of create artificially these pixel values, it kind of becomes this like really interesting colorful pattern. And I did the same thing for an even higher level layer, mixed 5B, and I made a huge step size because when I first did this I couldn't figure out what the pattern was. It looked like this weird scaly thing, and then after a lot of iterations and some blending, it generated this like really crazy turtle-like or maybe even fish-like reptilian eyeball feature layer. So low levels, lines, mid level, we have like interesting complex shapes like a flower petal is kind of more abstract. Then at an even higher level, we have even a higher level degree of abstraction where we have like eyeballs and actual parts of maybe animals that Inception has seen. It's really fascinating. This is just on random noise. Result B, I tried channel activations. It's kind of the same approach, but just a little more granular. So let's say we take the model 2D again, which is what we did up here. Which what we did for this one. And I just wanted channel 5. So there are 64 possible feature channels. The idea is each feature channel likes a specific feature, line, circle, shape, eyeballs, whatever. And let's pick 5. So the fifth one with the same other parameters generates, instead of a really interesting like nonlinear pattern, it's like this interesting contour like shape, seems to go left to right. So that's kind of what we'd expect. We'd expect this to be a component of a series of layers that generate here. These are the other 63 layers we didn't look at. So why don't we do the exact same thing though with the highest level layer that generated that weird insect pattern, except this one has 192 feature channels. So if you do this, this will generate kind of like ants. Looks like a very interesting set of ant-like or spider-like or bug-like bodies. So we did that with just, let's see, a slice of channels. This one's a little different than here because it's a higher level layer, and also we didn't pick one channel, we picked channels 40 through 70 out of 192. Whereas if we picked all of the channels, we would see this. So it looks like this subset of channels likes legs and ant-like things instead of more turtle level things, or rather maybe these features over-dominated these activations. Great. So with result C, let's try it on a real image. This is where I think a lot of the art kind of comes in. I downloaded off the internet a JPEG of the aurora. I think the aurora is really beautiful, and this is what we could plot. This is a really high resolution image. I think it's 1920 by 1080. And I thought, well, why don't we try to apply the flower filter to it, which is what we learned in just this overall layer activation of mix 3A by 5 by 5. That's what I did. It took a lot longer to train, and that's because bigger pixels means more computations through more convolutions. So even though Inception's efficient, almost 2,000 pixels still is really slow. It took maybe a minute or so to go, and you can see because I had a high level of step size, I made a lot of flowers to the point where at the very end of it, you almost can't really make out what the original image was. It looks like a dyed garden of flowers that may or may not be in the shape of some mountain with an auroral streak, which I thought was really interesting. So why don't we do that again, except for a different layer, for B, which through playing around, I discovered that it made dog faces, or maybe sloth faces. A little terrifying, but also interesting. And the more iterations you go, and the higher the step size, means you want the input image to activate the layer that you're optimizing against more, and thus, for this example, you see more and more eyes, or more eyes upon eyes upon eyes upon eyes. And that's the Inception name. Great. And then why don't we try a different one? So let's try a new image of the aurora here that I also got off the internet. Similar size, is pretty big. And let's try 3B 5 by 5 pre-ReLU, which is another layer. And as you could see, this one was a little lower level, so it liked less like eyeballs and shapes and more just like complex contours, lines. And this happened. So this is like a very interesting, more artistic filter, more abstract filter that you might see like in an art museum. And finally, the kicker, let's apply neural art on channel-specific activations. So this was all layer-specific. I just said for each a specific layer, give me all the channels and optimize it. For D, I was curious about that 40 by 70 channel split off of this high-level layer. I recursively optimized it, except I cranked up the step size to 20, still kept the blend factor low because I wanted kind of very intense patterns. And what I'm essentially doing is I'm applying, I gave away the surprise, I'm applying this feature hallucination to a real image, so I'd expect to see something similar, and at the end of the day, that is what we actually get. So as you can see, that neural layer tried to find whatever it could possibly detect that made it think of those insectoid legs. And if you scale as it scales up, blah, 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 you reach this really interesting high resolution auroral insectoid result, which is, scary but also beautiful at the same time. So that was great. In conclusion, there are a few important takeaways for computer vision practitioners and artists seeking some artificial intelligence hallucinated images. First, higher layers aren't always interpretable. Just because this was high doesn't mean I'm actually seeing insects, just a weird combination of insect-like shapes. I would have assumed that the final layers would be very clearly correlate with classes used during training. I'd expect the final layer, channel 1 to be dog, and channel 2 to be cat, and 3 to be mug or something. And that's actually not the case. So the layer learns whatever is convenient to you. It doesn't actually have to be bound in reality, but there is certainly a relationship there. Second, picking feature channels isn't always obvious. That does not seem to be an analytical or symbolic way to determine what channels map to what recognized features. Artists would benefit if they could say, I want to make something more dog-like, but they kind of have to poke around. Talking about dogs dominate a lot of layer-wise activations. And playing around, I saw a lot of dog-like things. And finally, there are also remaining questions around adversarial training of images that might deliberately confuse computer vision models into identifying the wrong thing. So if I can make a network hallucinate and thus say, be very confident that what it's seeing is what it's trying to see, then someone who might have a deceptive purpose might make artificial images with the purpose of frauding these vision models. So there's lots of research in this field, and it's an interesting time to work in computer vision and art. Thank you.